Hello students, today we are going to review elasticity of class 11. See now why this subject is required is in all design sections we need the strength of the material. How to design, which size of beam we have to design, we need the strength of this material. It is a property of the object by which it began its original configuration after removal of the deforming force. If I apply a force, we are all talking of rigid bodies. Rigid body means do not deform. It's not that it will never deform. If the force is more than its capacity, it will definitely deform. It will lose its configuration. But there is some stage where it can tolerate that load and it will come back to its original configuration. That is the property of elasticity. See, there are perfectly elastic bodies like quartz, phosphor, bronze. They immediately come back to their original position. They immediately come back to its original configuration after removal of the force. And again, there are perfectly plastic bodies like wax, paraffin, putty. Once you compress it, they will be remain the same position. So they are perfectly plastic, but they will not regain their position. See, steel is more elastic than rubber because if I stretch a steel within its elastic limit, it regains its position very fast. Rubber will stretch and may not, it will take time to retain its position. So that is why steel is more elastic than. See, for liquids, modulus of rigidity is 0. Rigidity means shear. There is no shear force in liquids. Some viscosity is there, but it's not a shear force. So, Young's modulus and rigidity only apply to solid material. They won't apply to liquids. Okay? The liquids only bulk modulus is applied. Now, what is stress? The internal restoring force acting per unit area of deformed body is called stress. The internal restoring force, suppose if I apply a force and body resists the force, then stress is developed. If it won't resist the force, it will simply deform, there is no stress developed in the body. So only the resistance to the external force developed by the body will make it under stress. So stress is equal to force per unit area. Force per unit, it is Pascal is the SI unit, Newton per meter square. Now there is a normal stress. Suppose if I pull a steel rod both sides, then it is subject to tensile. Same thing if I put it under a compression load, it is coming under compressive stress. In tensile stress, the internal stress will pull back the steel. In compression stress, the internal stress will push out the applied stress. Again, there is a tangential stress. Suppose if I apply a tangential load to a fixed body, there is a tangential stress. So what is strain is defined as? Strain is defined as change in the configuration by original configuration. It can be length of change, it can be area of the change, it can be volume of the change. So if I apply pressure, the volume gets reduced. If I reduce the pressure, volume gets increased. So there is a change in volume. Like there is change in area, change in length. This is the strain. Change in configuration by original. If it is length change by original length, we call strain. It is a linear strain, it is a areal strain, area delta A by A, and it is a volumetric strain or cubical strain. So now shearing strain. What is shearing strain? Angular displacement of the plane perpendicular to the fixed surface. This is a fixed surface. I have given a force here. There is a theta is the angular displacement. What is the units of theta? Theta is radius. It is a unitless component. Here you see these are all unitless. Strain means unitless. Delta L by L, meter by meter, unitless. Area meter square by meter square, unitless. Meter cube by meter cube, useless. Like that, shearing strain is also theta. Theta is deemed as, even though it radians, but it is not in ml length or some other unit. So it is a unit, treated as unitless component. So shearing strain is theta, is the angle theta it has deformed from the fixed surface. What Hooke's law says, within the elastic limit, so this is the elastic limit, within this proportional limit, the stress is directly proportional to the strain. It goes in a straight line. We can, once we know the slope, we know at what stress, how much it has got strain, we know. So that is, the stress is directly proportional to strain. When I equate it with a constant, the slope is E. E is called E. This is the constant, proportionality constant. This is the slope constant. D stress by D L is constant. So this E If it is length, it is called Young's modulus. If it is volume, it is called bulk modulus. If it is rigidity, it calls modulus of rigidity. So how the Young's modulus is defined? Normal stress by longitudinal strain. So we have said delta L by L is longitudinal strain. So normal stress is force by area divided by delta L by L. That means F into L by A L. F into del by A delta L. Okay. Okay. This is the L. So now what is bulk modulus is defined as F by stress, normal stress by volumetric strain. So delta V, normal stress is F by A by delta V by B. So pressure into F by A is pressure. In liquids, it is a force, stress is pressure. Pressure into V by delta V. So this is our bulk modulus. Now, what is compressibility? Compressibility is defined as reverse of bulk modulus. Bulk modulus is opposing the compression. But compressibility is allowing the compression. So it is defined as 1 by K. Modulus of rigidity is defined as tangential stress by shearing strain. What is tangential stress? Force by area. This is force, and the cross section is area, force by area. And what is shearing strain? Is delta theta. Delta theta is nothing but delta x by r. This is if h, let us say h into theta is equal to delta x, or d theta is delta x. So theta is equal to delta x by h. That is why delta x by h is shearing rigidity, modulus of rigidity. So F by A is the stress, by delta x by h is the shearing strain. What is elastic fatigue? Suppose if a body is subject to this force several number of times, it's not first time, it's 1,000 like that, then automatically it gets a stress. That's called fatigue. The values will come down. Its capacity will come down. So this is called elastic fatigue. Property of an elastic body, by virtue of its behavior, becomes less elastic under the repeated alternating deforming force called elastic fatigue. Now what is ductile material? Ductile material is having large plastic range. This is the plastic range. Which having large plastic range of ductile. Copper is a ductile material, silver is ductile, aluminum is a ductile material. Normally they are used to make springs and sheets. Now if you see the stress strain experiment, up to a value proportional limit as Hooke's law, their stress is directly proportional to strain. Beyond that also no plastic region starts. But the B is a elastic limit, yield point. So what happens from if you remove force from B, it will come back to the original shape. It may not be here. It is not directly proportional because stress is for a small stress there is a long strain. Okay, here stress strain are same, but here strain is increasing more for a small stress, increase in stress. But once we remove stress here, it will retrace back. But after this yield point, if I increase further stress, still it will retrace back, but it will not retrace back in this line. It will retrace back like this. That means this permanent deformation will be there. Suppose this is L. So if I go beyond this stress limit of the material, it will become L plus delta L. Next time when I do experiment, it will be L plus delta. Again I have to do in this line. Like that, it will be permanent deformation will be set in that if you cross this limit. So all our designs section will take this as limit and give some factor of safety, maybe 1.5 factor of safety, 2 factor of safety. That means our design limit is half. 2 factor of safety means half. 1.5 factor of safety means this is my design limit for the material loading. So like that, so we will not try to cross this zone if I want a safe loading design. So now if I go beyond C, it will not even come back to this permanent deformation. It will simply with small rise in stress. What is the stress rise from here to here? Very small quantity, but strain. It completely elongate. So we'll go to a ultimate stress point. From this stress point, ultimate stress point. This is ultimate stress point. Then automatically it will goes to the breaking area. This is the fracture point. So at fracture point is less than the ultimate, it will continue to slog and it will break here. Area will be so less, it will be subject to fracture. Okay. See, we are dealing with stress and strain, not force and strain. Because force depends on area of the material we have chosen. It may be 1 mm, 2 mm, 3 mm, 4 mm dia. But since stress is taking care of all material, because F by area is stress. Now, we know brittle material, they immediately break. They don't have any plastic region. The material which show very small plastic range are brittle. Like glass, like cast iron, they have very small plastic. Elastomers is they stretch too far. The materials for which strain produced is much larger than the stress. For example, rubber and even blood carrying vessels, they're all having elastomers. Elastomers have no plastic range. They simply stretch and they break out. If it is more than this, there is no plastic range. They stretch more. Now, how once if anything I am applying force and it is under tension, there is energy stored in this like a spring. Energy stored like a spring. What is this energy defined as? U is integral F dot dl. Integral F dot dl. So, why we defined Young's modulus as F by A into delta L by L. I am representing delta L as small l. Okay, F by A by L by L. That means F capital L by A small l. So if I want F here, the other things will go the other side. Then it becomes Y A L by L into delta L. If I integrate, L delta L becomes L square by 2. So half Y A L square by delta L. This is the energy stored in a stretched string. Suppose half YAL by L into L. This same thing. YAL L square I have given L by L into L. So when I further rearrange with 1 by area into area, 1 by L into L, and I rearrange, what I got? Half this is stress, this is totally stress, this is force by area, stress, and this is L by L is strain, AL is volume. So half stress, strain, volume is the energy. So energy for unit volume is half stress into strain. Or if I put stress is, what is stress? This F by A is stress, stress by strain. So stress is equal to Young's modulus into strain. So half Young's modulus into strain square. So these are all interrelated, one on another. So what we got here, energy stored per volume is half stress into strain, which is nothing but half Young's modulus into strain square. Half Young's modulus into strain square. If you see, half Young's modulus into strain square is resembles like other energy stored per unit volume. Say for a spring it is half kx square. For electrical, half epsilon naught E square. For magnetic, half B square by mu epsilon naught. They are all similar representation of energy stored per unit volume. Okay, we will go to. Suppose what is the thermal stress? Suppose this rod is there, I fixed both ends and I supplied heat to it. So it try to expand. If it try to expand, but it will not allow it to expand. So there are stresses developed. Thus stress is thermal stress is force by area is equal to y alpha d theta. What is this? Y is Young's modulus. Alpha is the coefficient of linear expansion. Delta theta is the temperature difference. So then we say how much it is. Suppose if it is not there, then I heated up. Then this rod will give an extension. What is this extension? L alpha d theta. Delta L is equal to original length into alpha is a coefficient of linear expansion into temperature difference. If delta L by L, if I take this L under this is strain. The strain is alpha d theta. That is why force by area is equal to Y into strain. Strain is alpha d. This is alpha d theta. This is nothing but alpha d theta is nothing but strain. Delta L by L. Otherwise, delta L is L alpha d theta. So similarly for gases, it is subject to volumetric expansion, coefficient of volumetric expansion, that is K gamma d theta. So alpha, beta, gamma is the alpha is the linear coefficient expansion, beta is the areal, and gamma is the cubical or volumetric expansion, coefficient expansion of material. This is how the rigidity modulus and Young's modulus vary with temperature. They also vary with temperature because with the coefficient of linear expansion. Now let us understand what is Poisson's ratio. Suppose if I pull a string, the length of the string is increased and at the same time the radius is reduced. So its length increases, but its radius reduces because volume is same, material is same. Now no material is getting added or removed. So as the length increases, its radius increases. The radius getting decreased. So the ratio of lateral strain to longitudinal strain. What is lateral strain? Delta R by R. Why put minus? Because as length increases, delta R reduces. As length, suppose a compressive force. As length reduces, delta R increases. So one of these is getting minus delta R by delta L by L. Delta L by L is longitudinal strain. So the lateral strain delta R by R divided by longitudinal strain. Longitudinal is positive because when I'm pulling it, delta L is positive, delta L by L is positive, but radius is negative. If I put in compressive stores, compressive pressure stress, delta R is positive, delta R by R is positive, but delta L will be negative. So finally it is a negative value. Normally this lies between -1 to zero point 0.5. This is the value of Poisson's ratio sigma. It's called sigma. We represent Poisson's ratio. Now there is a relation between the rigidity modulus, bulk modulus, Poisson's ratio and Young's modulus. There are four relations, but we remember only two relations we have to by heart. Other two are derivative of the other. So what is this? Young's modulus is equal to 3 into bulk modulus into 1 minus 2 sigma. Sigma is Poisson's ratio. Similarly, Young's modulus again is 2 into rigidity modulus into 1 plus sigma. So if you take alpha is to beta is to gamma, the coefficients ratio, they are in 1 is to 3 is to 3. So if Young's modulus represents alpha, so the K is volume, bulk modulus is volume. So it is representing 3. That is why it comes 3K. So Young's modulus is 3K into 1 minus 2 sigma. Similarly, rigidity, let us say it is assuming second one. So Y is 2N into 1 plus sigma. Now how this equation has come? Y and K. So out of these two, if I remove sigma and make Y as subject, I will get this equation. Again, out of these two equations, if I remove Y and make sigma as subject, I will get sigma and K. So these are all derivative from these two equations. So we have to by heart Young's modulus is equal to 3K into 1 minus 2 sigma and Young's modulus is 2 rigidity modulus into 1 plus sigma. Okay, we'll go to it. What is the isothermal elasticity of a gas is stress by unit strain. That is pressure. Stress is nothing but pressure. Force by area is pressure. Is isothermic means temperature is constant. Isothermic means temperature is constant. So P is the isothermal elasticity. If you go to adiabatic elasticity is gamma P. Because the compression is not isothermal, compression is adiabatic because we don't allow the heat to go outside. So it will be an adiabatic compression, then it is gamma. This is the Laplace correction, this is Newton's assumption. This is the first base is given, then Laplace has corrected to gamma P. Why we use this? This is used to find helpful in the sound in the medium. They give velocity of sound in the medium is root of gamma P. So that is why these two are useful. Now let us see how a cantilever is being. This is a cantilever supported at one end. So the weight of the cantilever is at CG area. Here is CG. Weight of the lever is acting. So the cantilever tries to bend because of the self weight. The bend is, the strain is around delta. How delta is defined as weight into this is the L of the cantilever, WL cubed 3y Young's modulus into I. I is moment of inertia. It is not with mass, it is area moment of inertia. I is 112 BD cubed for a rectangular box. 112 BD cubed for a rectangular box. So WL cubed by 3yi. If it is simply supported beam, suppose the beam is simply supported, it is not hanging from one end, it is both sides supported, and on its self weight, or if I put a weight here, suppose I am putting a weight here, W weight plus self weight. How much is the delta is going to bend? WL cubed by 48yi. So 48 means 12, 4 times. So a simply supported can take 4 times load than a cantilever. Okay, that is why most of our designs are simply supported. Cantilever very rare area. We provide this also with sufficient this wherever required. But otherwise we go for a simply supported design support. So if you take a loaded represent delta WL cubed 4YBD cube. Why 4y? Because 12 by 1 BD cubed by 12, this is 3y. 3 by 12 by 3 is 4. 4y BD cubed. Similarly, this is 48, so 3 by 48 is 4 by 48 is 12. Because for a cylindrical, it is BD cubed by 4, pi r square by 4. So it comes WL cubed by 12 pi r square. This is WL cubed by 4 pi BD cube. Okay. So depending on the section, the delta varies. If it is a bigger section, delta is less. If it is a cylindrical, some other delta. So we have to use this areal moment of inertia of the respective beams. Now let us see a shear strain. Suppose this is fixed at the top end and I have given a couple force into radius, a torque onto this. So it has twisted to a distance of x. So what is this x? This x is r into theta. X is r into theta. But what is the strain? Strain is defined as this phi. The phi is equal to r into theta by L. So how the phi is strain, the shearing strain is coming up? R theta by L. This is R theta and this is L. So R theta by L strain. So here the strain is phi. Phi is unitless radian degrees. So radius. Suppose what is rigidity modulus? Stress by strain. Stress is F by A. Strain is theta. Theta is phi. Strain is phi. So F by A into delta X by H. This is assumed as delta X. Now we have a torque per unit theta. This is a torsion strength of even a wire or a cylinder. We have a torsion strength coupled for theta. It is defined as when we substitute above things, when I put area as pi by r square, rigidity modulus pi r to the power of 4 by 2L. L is the height. L is the height. So this is a torque per unit length. Now let us see some problems. Suppose this ball, it is swinging from top. It has come like this. So what is the limitation? So ball weight is 10 kg and it is moving with 10 radians per second. So when 10 kg will give a load of 10 into 10, 100 newtons. The 10 radians will give a m r square omega. What is this? It will give a centrifugal force also. So if I put m, when r is 1 meter, so r square also 1 meter. m r omega square. So 10 square. Okay, m r omega square. mv square by r, so it is m r omega square. So it comes to 10 into 100, so 1100 newtons. So what is the stress? Stress by strain. F L by A delta L. If the length increased by 10 mm from the original of 1 meter, what is the Y? We have given area. So if I submit, the Young's modulus of this rope wire comes to 11 into 10 to the power of 9 Newton per meter square. Because Young's modulus and stress are same units. Stress by strain. Strain did not have any units. So stress is force per area. So 11 into 10 to the power of 9 Newton per meter square is the Young's modulus. So understood? What was given? Ball is swung. Ball weight. We have got omega. Length increased by it is delta L 10 mm. It is in terms of mm. From 1 meter. So the area is given 10 to the power minus 5 meter square. So we have to find. So what extra thing is, I have clubbed two things. One is the weight of the ball plus mv square by r. 6 mg. Comes to around 6 mg. So weight mv square by r. Now this is another example. We have three bodies. 1, 2, 3. Length is 0.1 meter. This is 0.2 meter. This is 0.2 meter. Their areas 10 to the power minus 4 meter square. 10 to the power minus 2 meter square. Their Young's modulus. This is 2.5 into 10 to the power of 10. This is 4 into 10 to the power of 10. This metal is 2 into 10 to the power of 10. What is the subject? Then 50 kg is hanging from the bottom. So 50 kg hanging. So what is the total extension? Because of the 50 kg weight by the 3 things. So 50 kg means delta L is F by A by Y by L. This is a delta L. Because otherwise Young's modulus is F by A by delta L by L. So delta L has come this side, Y has come to other side. So when I substitute these figures, force is 50 into 10, 500. So when I substitute force, and the length is, we have 0.1 meter, area is, we have 10 to the power minus 4, and we have Young's modulus here. So I'm getting 20 to the power minus 6, this extension, and this extension is 25 to the power minus 6, and this extension is 15 to the power minus 8. When I add all the three, 45.5 to the power minus. This is the total extension of the three bodies together when I subjected to a load of 50 kg.